Hey guys, this is video 14 on the Fundamental Theorem of Calculus Part 1 and Part 2. Starting off with Part A, Fundamental Theorem of Calculus Part 1. What is the Fundamental Theorem of Calculus? Well, that's what allows us to solve our integration for those limited values that they give us. So say I have the integral from a to b of f prime of x, so I have some derivative, some rate that I'm finding the integral of. I have that limit from a to b of f prime of x dx is going to equal to the antiderivative, so find the antiderivative, and then substitute in your top limit minus your bottom limit. Okay, so when you're doing the fundamental theorem of calculus, think about it in terms of first you have to integrate, then you have to substitute the top limit first, so find f of b, and then find the bottom limit, f of a, subtract those, and then step 3 is to simplify. Sometimes the fundamental theorem of calculus part 1 helps us to find area given an initial condition. If you're moving right on the x-axis, so like for example, I have f of 4 and I want to find f of 7. I'm moving from 4 to 7 on the x-axis. That means that I'm going to add the integral in addition to my initial condition that I already have. But if I'm moving to the left, so say I have f of 4 and I want to find negative 2, f of negative 2, then I'm going negative 2 to 4, I'm going backwards, so I'm going to be subtracting the area, the integral that I'm going to be performing from 4 to negative 2. So let's do an example of this. So in example 3, I don't know why it's called example 3, it just is. The graph of f prime is shown. Use the figure and the fact that f of 4 is equal to 5 to find f of 0. So keep in mind that f of 4, this is the graph of f prime, so that's why f of 4 is not actually equal to 5 on f prime. But f of 4 is that functional value on the antiderivative of f prime. So I can use that knowledge, my initial condition, to find, okay, well, what is f of 0? So f of 0 is going to be equal to f of 4. Well, I'm going from 4 to 0. So I'm going to be subtracting the integral from 0 to 4 of f prime of x dx. So how does this formula relate to the one I gave you in the beginning? So f of b minus f of a, those are after I've integrated, right? So those are my f of 0 and f of 4. So I basically just said, okay, I have f of 4, which is going to be my f of b. And so like this is like f of 4. This is like f of 0, my bottom limit. And then I have my integral from 0 to 4 of f prime of x dx. So I'm basically saying, okay, let me subtract this f of 4 to the other side, put it with this one, but then I have to also divide by a negative 1 to get rid of that negative in front of f of 0. So my signs would change here. That's going to give me this formula here. So I'm just manipulating that formula that I have, that fundamental theorem of calculus, to find one functional value given my initial condition or one of my functional values. So if I solve for this, this is just going to be 5 minus, well, the integral from 0 to 4. 0 to 4 is just this area in here, so the area under that curve is 8, so 5 minus 8 gives me negative 3. So that means that f of 0 is equal to negative 3. Alright, let's try another one. So now I have f of 4 equals 5, and I need to find f of 7. So I'm going from 4 to 7, so that's going to be adding more area. So I have f of 7 is equal to my f of 4 that I already have, plus some more area, the integral from 4 to 7 of f prime of x dx. So same thing as the previous one, I'm going to solve this by saying, okay, well, f of 4 is 5, I know that. That's my initial condition, plus the integral from 4 to 7. Well, 4 to 7, that area is 4, but it's underneath the curve. It's underneath the x-axis, so that curve's area is going to be negative, so this is actually 5 plus a negative 4, which means that f of 7, the functional value for that, is actually equal to 1. So by using the initial conditions, we can add some more area or take away some more area so that we can find another functional value. Now let's think about this in terms of word problems. So a pie with a temperature of 95 degrees Celsius is put into a 25 degrees Celsius room when time is equal to 0. The pie's temperature is decreasing at a rate of R of t equals 6e to the negative 0.1 t degrees Celsius per minute. Estimate the pie's temperature when time is equal to 5. Okay, so time equals 5, that's like my x value, right? Because time is in my rate, R of t. And so my R of t, that's my rate, it's decreasing, so keep in mind that's going to be a negative rate because it's decreasing. And what's my initial condition? So they gave me, at f of 0, what's the pie's temperature? They actually tried to trick me on this one. It's 95 degrees because it's put into a 25 degree room, but the pie's temperature at time equals 0 is 95 degrees. Oh, that shouldn't be F, that should be R. Okay, and then the one I want to find is R of 5, and I want to know what the temperature is then. So I'm going from 0 to 5, which is adding more area, or adding more time for that pie to cool down. So I'm going to have my fundamental theorem of calculus says that if I want to find R of 5, I can take my initial condition, R of 0, and I can add, because I have from 0 to 5 is going to the right, so I have to add the integral from 0 to 5, that change in temperature, of negative 6e to negative 0.1 t, degrees Celsius per minute. So remember, that also reminds me it's a rate, degrees Celsius per minute. That's going to be in the units for a rate. And then I can solve this. So I have R of 5 is equal to R of 0 is 95, plus that integral, I'm just going to use my calculator for that. I could solve it by hand, but for the interest of time on this video, let's just use our calculator for this. And in my calculator I have negative 23.60816. Remember, I'm going to go to 5 decimal places before I round anything. And when I add those two together, my pie's temperature at R at time equals 5 is 71.39183. I'm just truncating here, I'm not rounding. Okay, so now I'm really glad that we can solve it, but I also want to be able to explain it using my NUT, right? Noun, unit, time. So how could I state my final answer using noun, unit, time? Okay, so I have my sentence here, and I have the pie's temperature is, so that's my noun, the 71.39183, that's gone truncated to 5 decimal places, sounds good, and that's my unit, degrees Celsius. When time equals 5 minutes, that's my time. So I restated my final answer using NUT, the way we always justify things in calculus. Let's do one more about position. So in this example, a particle is moving along the x-axis and has position x of t at time t with the velocity of the particle v of t equals 5 cosine of t squared. At time equals 5, the particle's position is 3, 0. Find the position of the particle when time equals 7. Okay, so the reason I know that this is a fundamental theorem of calculus question is because it's telling me about a rate. A rate is my velocity when we're talking about position, velocity, and acceleration, right? Because position is x of t, velocity is v of t, and acceleration is a of t. So velocity is the derivative of my position. So I know I'm given a rate. I'm also given an initial time for the particle's position, and position is the one before the velocity, so I have to use an integral to get that. And I'm given a new time that I need to find. So I'm given my x of 5. The position at 5 is equal to 3. And the position at 7 is what I want to find, right? How do I know it was 3? Because on this, if this was a graph, 3, 0 is right there. So on the x-axis, it's at 3. And remember, it's only moving along the x-axis, so this motion is only going to go left and right. So since I'm going from 5 to 7, I'm adding more area, so I'm adding the integral. I'm adding more change, my total change. So I have the integral. Let's start with a full equation. So we need to find the position at 7. is equal to the starting position, which is at x of 5, plus more total change between 5 and 7, so that integral from 5 to 7 of 5 cosine of t squared. Okay, so I'm just going to solve this by using my calculator. X of 5, my position is 3, plus the integral from 5 to 7 of 5 cosine t squared. Oh, dt. Can't forget that. That's going to give me my negative 0.26566. So adding that with 3, my position at 7 is going to be 2.73433. So let's state this using nut. So the position of the particle is, I put it as a coordinate point because there are no units on this one, and the other one was stated as a coordinate point. So I figured there. Then I figured I should also state mine as a coordinate point. So 2.73433, comma 0, when time equals 7. Again, time equals 7 has no units, otherwise you would make sure you had them. So I have the position of the particle, that's my noun, my unit, and my time. That's a great nut. Okay, so let's move on to the second fundamental theorem of calculus. The second fundamental theorem of calculus, part 2, says that if I take the derivative of this integral from a to x of f of t dt, then my answer is just going to be f of x. If I switch those limits of integration and I change the a and the x, remember anytime I'm switching my limits of integration, then I'm really just making the answer negative. So this is the same exact thing, it's just going to be a negative f of x. So I'm just taking that x and I'm substituting it in for the variable of my function. Now part 2 with the chain rule is a little different. So if there's a function up here instead of just x, then I can, yes, put that function into my variable, but then I also have to do the chain rule. So this would turn out to be f of u of x times the derivative of whatever that top thing is. So I put u prime of x. Let's do an example. So here are 3 examples. The first one, whenever you see this d dx and an integral, you should immediately be thinking fundamental theorem of calculus part 2, and that means that I'm probably just going to be able to substitute whatever's up there in for my variable. So I have here, this is going to be the square root of 4 minus x squared, and that's just going to be my answer by itself. That's good. Same thing for the other one. We have an 2 to x, and we have the integral and the derivative put together, so that x is going to go right inside of that secant t cubed. It's going to be secant x cubed. And the third one, that one's a little different. Look what's here. We don't have an x, we have an x cubed. So this is my chain rule. This is when I take the derivative of x in a and b, that was just 1. So this is like multiplying it by 1. Multiplying by 1. It's not going to do anything to it. But for this one, I'm going to have to multiply by that derivative of x cubed. So first I'm going to substitute in for my t. So I have my answer is going to be 3 over 1 plus x cubed times the derivative of x cubed is 3x squared. So let's clean this up a little bit. I'm going to multiply that 3 and 3. This gives me 9x squared over 1 plus x cubed. So second fundamental theorem of calculus is very easy to recognize because a derivative and an integral put together, that's going to be your hint that this is the FTC part 2. And you just have to remember, if it is a chain rule, if there is something there, you have to make sure that you're substituting it in and then taking the derivative of whatever you are substituting in for. Also, if the x is on the bottom, which there was no example like that, but if I had the derivative with respect to x of the integral from x to 2 of secant t cubed dt, then you would be substituting in the 2, but we don't want to do that. We want to substitute in x. So I have to flip these, so this is going to be negative secant x cubed. Just as a reminder, that's also an example that you could see.